We today are going to apply vectors and look at what vectors do for us in different scenarios. So our first one, an airplane with a speed of 150 kilometers per hour is pointed directly west. There is a wind blowing out of the southeast towards 300 degrees at a speed of 20 kilometers per hour. What is the magnitude and direction of the resulting vector representing the motion of the airplane over ground? So let's think about this. Okay, if you're, picture yourself driving down the road. If there's a crosswind, you end up pointing your steering wheel in a slightly different direction. Well, that's kind of what's happening here. So the motion over ground means we're looking for what's actually happening. He's pointed west, but the wind is pushing him. I'm going to draw this tip to tail first just to kind of show you what's going on, but then we're not going to mess with that. Okay, so you don't need to draw this if you don't want to, but we're going directly west. So this airplane's going directly west at a speed of 150. And then the wind is coming out of the southeast towards northwest, which is going to be at 300 degrees. So this is, from here to here is 300. So the out of the southeast, but it's always a toward thing. So what's actually happening is, this is what's called a tailwind. The wind is making it so the plane isn't going directly west, it's going slightly north of that. So our job is to figure out how fast, because the tailwind is going to make him go faster here, and then what's the actual angle. Okay, so again, I'm going to show you this using the I and J notation, but if you have a different way to organize it, that's totally fine. So I'm going to draw each of my vectors. I've got my vector that's going directly west. I'm going to call this vector P. So this is 150. And then I'm going to have my wind, which is going 300. Call this W. So that's 300. Okay. Then we're going to break them down into their components. So P, we don't really need to do too much thinking. This one only has a horizontal component, and it's 150. Okay, my wind is going to be a negative positive, but I need the reference angle. So the reference angle, if this is 300, that makes this angle here 30. So my components are going to be negative. The magnitude was 20. 20 cosine the reference angle 30 in the x direction, positive 20 sine 30 in the j direction. Use your calculator. I trust you can do that. Okay, so that's my components there. Now I'm going to add those together. So add the 150 and the 17, so that's going to be negative 167.320. And then we just have that 10 in the y direction. Now we're going to find the magnitude and the direction of our resultant. So the magnitude, which is going to be the speed that the plane is actually going, is going to be the square root of 167.320 squared plus 10 squared, which gives us 167.619. This would be in kilometers per hour. So like I said, this has a tailwind, so we're going faster. For the direction, okay, what we have is a negative 167 and then a plus 10. That's my result. So we're going to start with the tangent inverse. Ignore the negative. We don't care about the negative here. That gets me 3.420. Okay, but that's not the angle that we want. We want the bearing. I want the angle from here to here. What I have is the 3.4. So what I'm going to do is add, in this case, 270. And like I've said to you guys, this is going to depend on what convention we're using. Is it a bearing? What quadrant you're in? So there's not really something you can memorize to do this. You just have to think about the situation. Okay, so we don't have to say, we understand this to be a bearing because that's how the problem was given to us. Let's do another example. All right, we've got another plane with some wind. So plane travels 300 miles per hour on a heading or a bearing of 14 degrees. And it's convention to use 3 decimals when you're talking about bearings. I'm not going to require it, but that's just how it works. The wind is blowing out of the southeast towards 320 at 86 miles per hour. That's a pretty fast wind. What is the ground speed of the plane, and what is the course over ground of the plane? Start with my pictures. So I have my plane is going at a bearing of 14 degrees. Okay, so this angle here is the 14. I'm going to again call that P for plane. The wind is going out of the southeast towards 320. Okay, so this is 320. We're going to break them down into their components, so I need the reference angles. If this is 14, that's 76. If this is 320, that angle is 50. So the first one's positive. So this will be 300 cosine 76 in the x direction, or I, plus 300 sine 76 in the j. And I'm just going to write this over here. So it's a positive 72.577I plus 291.089. The wind is a negative positive. So negative 86 cosine 50 plus 86 sine 50 gives us a negative 55.280 and 65.880 in the j direction. Okay, now I'm just going to add those together to get my resultant vector. So when I add 72 and the 55, we get 17.297, and then we add those two guys together, we get 356.969. Okay, so our magnitude is going to be the ground speed. Okay, so just put that in the Pythagorean theorem, and we get 357.388. This will be miles per hour. This is our ground speed. Okay, then we want to know, where is this plane actually going? So our components we have are positive 17 point whatever and positive 356. So this is the vector. we'll start with our tangent inverse. Okay, this gives us an angle of 87.226. Okay, but again, that is the reference angle. This angle is the 86. What we want is the bearing from due north. So for this case, I'm going to subtract our answer from 90. Okay, this gives me a course or a bearing of 2.774. So almost due north, but not quite. So our speed and our course over ground, where the plane is actually headed. Okay. Our next example is a pretty standard physics type question. Two forces are acting on an object. Force 1 of 25 newtons pulls at an angle of 20 degrees above due east. A force F2 35 newtons pulls at an angle of 60 degrees above due west. So let's draw these guys. Okay, so 20 degrees above due east. So that's going to be 20. So that's going to be my first force. And then this next one, 35 above due west. Okay, just like always, we're going to break them down into their components. We already have the reference angle, so we're good there. This one's a positive positive, so that's going to be 25 cosine 20 and 25 sine 20. And then 8.551. Okay, then we'll do our second force. This one's going to be a negative positive. So we're going to have a negative 35, no, I wrote that 30. This is 60 degrees here. Cosine 60. Okay, so that angle is 60. Then calculator, we get negative 17.5 in the x direction and 30.311 in the y. Now, we'll add those together. Okay, we'll find the magnitude. Is 39.321. This will be in newtons. We also want the direction. So anytime it says the resultant force, the resultant is a vector, which means we want magnitude and direction. So I'm going to do tangent inverse of my y over the x. This gives me 81.235 degrees. Now let's think about what we need to do. This problem said above due east and above due west. Well, since this one's a positive positive, we found the 81, and we can just say above due east and call it good. All right, another physics situation. We have 3 students are pulling on a chair. Einstein is pulling with a force of 5 newtons, and Copernicus is pulling with a force of 4 newtons. The angle between their ropes is 120 degrees. What force does Marty have to pull his rope on so the chair doesn't move? What angle should be formed between the other two ropes? So here we haven't been told, what quadrants we're in and whatever. So what I'm going to do, I'm going to sketch all these together in this case. To make my life easier, I'm just going to put one of them on the positive x-axis. Okay, so I'm going to say this is Einstein, and he's pulling with a force of 5 newtons. Then we have Copernicus is pulling with a force of 4 with an angle between them of 120. So that's Copernicus. He's pulling with a force of 4. This angle in here is 120. So you can pick where to put it. Like I said, positive x-axis is the easiest. Now if we think about this situation, the third party, if this guy's pulling here and this guy's pulling here, in general, the third rope is going to have to be somewhere here. Okay, we know that to be true. So let's break this down into vectors and see what we can do. Okay. My Einstein here, I just have going component-wise just 5 in the x direction. Copernicus, if that's 120, this angle is going to be 60, and then I'm going to have a negative positive. So it's going to be negative 4 cosine 60 in the I direction, and positive 4 sine 60 in the y direction, or j direction, which gives me negative 2i plus 3.464j. So I'm going to add these two together. So I add the 5 and the negative 2 to get 3 in the x direction, and then that 3.464 in the j direction. So that's what's happening to these two ropes. These two ropes are pulling at a positive 3, positive 3.4, so it should make sense. That's what they're headed. Now we're going to introduce Marty. Okay, if E plus C, if Einstein and Copernicus add up to this vector, what would the components need to be for Marty for nothing to be happening? Well, it's going to be a negative 3i and a negative 3.464j, okay, which matches our picture. Okay, we said it's going to be somewhere down here, so we initially intuitively understood if I put this one here and this one here, this one's going to end up in the third quadrant. Okay, now we're going to break this vector down. So the magnitude, the force that he's going to have to pull at, is going to be approximately 4.582 newtons. Okay, and then the angle. We get an angle of 49.106. Okay, now in this case, what do we need to do in this problem? We're trying to get the angle to each of the ropes. The 49.109 is the reference angle. That's this angle here. So what do I need to do to get to the other two ropes? Well, let's start with Copernicus. If I want this angle here, I'm going to add the 49 plus the 60. So I'm just going to say 2c is 49.106 plus 60. So that's going to be 109.106. Okay, so that's our first angle. Then if I want this angle to E, Okay, well, again, if I know this is 49, for this angle, I'm going to subtract from 180. Which gives me 130.894. Now it should make sense why this angle is bigger. If this force is bigger, then he's going to have to lean a little bit towards Copernicus's side and to make everything 0. Okay, so in this case, we just conveniently put it on the one of them on the x-axis, and then go from there. All right, so we have one more example here. The ship USS Enterprise sets sail from Honolulu on a bearing of 65 degrees, back to bearing. It is traveling at a constant speed of 35 knots. After 2 hours, the boat changes course to a bearing of 300. 1 hour after the change in course, the ship needs assistance from the Coast Guard operating out of Honolulu. What is the distance and bearing from Honolulu to the USS Enterprise at this point? All right. So part 1 of our journey. They set sail at a bearing of 65. So they were going 65 degrees. This is 65. Okay, at a speed of 35 knots, which is nautical miles per hour, so it's a speed for 2 hours. So if they're going 35 nautical miles for 2 hours, they are 70 nautical miles from Honolulu at this point. And they decide to change course a little bit here. Part 2 of the journey, they start going at a bearing of 300. So 300 that's 300, which makes, I'll just label it 300 for now. And then they'll only do this for 1 hour. So this one's only 35 nautical miles long. Okay, so let's get some reference angles so we can break this down into components. So this is 65, which makes this 25. This is 300, which makes this 30. Okay, so we're just going to break each of them into their components and add them and turn it back. So this is a positive positive. So this will be 70 cosine 25 plus 70 sine 25. Okay, so get that. Part 2 of our journey is a negative positive, so negative 35 cosine 30 and 35 sine 30 in the j direction. We'll add these together to get our final components. Okay, we'll put this in the Pythagorean theorem to get the distance. So the distance is going to be 57.571 nautical miles away. For the direction, we get 54.867. But let's go back to the picture to see what we need to do to correctly answer this question. So we're at a positive 33 and a positive 47. We found this to be 54. What we want is the bearing from due north. So we're going to take our answer, subtract it from 90. Sorry, from 90. So our bearing, where we're going to send the Coast Guard, is at a bearing of 35.133 degrees. Okay, so those are different applications of vectors.